All right, I think we're all set here. Oh, I feel all pressured now. It's like this whole different feeling. It's like now I'm being recorded. Wow. I won't. All right, so question 5.
What about it?
This is from Alright, so this is our scenario here that we're dealing with. A string is tied to a 4.4 kilogram block and a 120 gram hanging bucket. Students are going to add washers, they're 20 gram washers, one at a time to the bucket. The students are unaware that the coefficient of static friction for the block on the table is 0.42. But we know that it's 0.42. Okay, they don't know that, but we do. What's the maximum force of static friction acting on the block? All right, they don't give us kinetic friction, they just give us static friction here. Any thoughts? What should we do here? Don't be shy just because it's recording. Yeah, force of gravity acting on which block? Well, we are going to need eventually the force of gravity acting on the bucket, but for this question, the friction only acts between the 4.4 kilogram block and the ground. So we'll call this block 1, and we'll call this 2. All right, so FG1, just 4.4 kilograms times 9.81. So 43.1 newtons. Okay, so the question's asking us to find the force, the maximum force of static friction. So all we have to do here, since we're on a level horizontal surface, we know that the normal force is equal to the force of gravity.
Wait, if we aren't on a level horizontal force?
If you're not, then the normal force is perpendicular, remember, to the two surfaces in contact.
Oh.
Okay, so all we have to do is multiply that by the coefficient, and we've got the actual force of static friction. And it's 0.42. Laura, what's the unit on the coefficient of static friction? 1. There is the 1. Good. That's it for question A. So you could apply a force of 18.1 newtons onto that block without it moving. Okay, we've done these questions. Sorry, what's that? No, that's like as soon as you hit 18.2, it's going to accelerate. Yeah, and then kinetic friction takes over. So all these questions that we've done up until now have had frictionless surfaces, right, between the table and the block. So now we're just adding one level of complexity where we're dealing with friction between the surface and the block. Okay, what's part B asking? So how many washers does that translate to putting in the bucket. Now, the nice thing about this first part of the problem, if I look at a free body diagram of the bucket, if there's no acceleration, the net force equals 0. Then what do we know about the force of tension?
Equal to the force of gravity.
Yeah, Evan. Equal to the force of gravity acting on the block. Okay, so all we have to do to solve part B is to recognize that this force of tension has to be equal to that 18.1 Newton static frictional force. Okay, and that's going to be the maximum force that we can apply without moving the block on the table. All right, so that also is going to be equal to the force of gravity acting on the bucket. This is going to be our plan of attack for part B. So all of these forces are at this point going to be equal. Yeah.
I was gonna ask if we do we just multiply the washers by the force of gravity to get.
Yeah, we're going to be
static
working
unit?
back. That's exactly right. We're going to be working backwards here. So 18.1 newtons being the force of gravity is equal to the mass of the bucket, the loaded mass of the bucket that we're solving for, times g. Oh, might as well sum that up. All right, so if we divide 18.1 by 9.81, we end up with a mass of the bucket of 1.85 kilograms. I should put that 2 subscript all the way through because I labeled the bucket mass number 2. What's that? Not quite. We have to subtract the mass of the empty bucket first and then divide to get the number of washers. Okay, that's going to be the mass of the loaded bucket with a bunch of washers in it. To figure out the mass of the washers, you got to subtract the empty bucket mass. And this is the empty bucket mass. Minus 0.12 gives us 1.73 kilograms worth of washers. Now just divide it out and then round down. Yeah. So Maria, you're exactly right. We're going to take that mass of washers, 1.73 kilograms, and divide it by 0.02, 20 gram washers. So number of washers. So 1.73 divided by 0.02 gives us 86.5. Right, so you got to rip 1 in half with your raw strength. We're just going to round down. Right?
Don't you have to round it up?
No, if we want to know the maximum we can add without accelerating the system.
Oh yeah, okay.
So if we go up to 87, then the system's going to start accelerating. All right, so as soon as we added that 87th washer, then we'd overcome the force of static friction, and we'd cause the system to start accelerating.
And then a 4.4 kilogram block would hit someone.
Yeah, hopefully we can catch it. Okay, will this investigation yield an accurate result if they use it to find the coefficient of static friction? What do you guys think? If they actually do this to try and find the coefficient of static friction between the block and the table.
It would be sort of accurate. 0.5 there would throw it off.
Yeah, that's actually a pretty good experiment. The only issue is the fact that you're going up by discrete amounts every time.
You better use sand.
Yeah, that would be even worse. Okay, so C. Okay, so if you're doing this really accurately, you'd be slowly, continuously increasing the force, maybe using a gear to increase the tension. And you'd be measuring the tension using a force sensor. And that way you could actually figure out what at the exact second when the object slipped, when that 4.4 kilogram mass slipped.
Couldn't you also just use sand?
Could you use what?
Sand. That's such a small
Yeah, that would work too. Or water, even better. It's a good idea. That's way easier than using a gear and a force sensor. Just fill it up with water. Okay, not quite done yet. We're still at part B. Okay? So now we've gotten to the point where we've just added that 87th washer. And now the whole system starts to accelerate. They want to figure out what that acceleration value is. So if we draw a free body diagram of the entire system.
Again.
No, that's a system diagram, Evan. Okay, system diagram. This is a free body diagram. This looks weird, but I'm going to simplify the system. If we look at the system as a whole, it's easy to simplify it to forces to the left and to the right instead of kind of like down to the right and left and up. Okay, because the system acts in two different directions. If you look at it from the bucket's point of view, it's up down. If you look at it from the block's point of view, it's left right. So if we actually if we want to draw a free body diagram of the system as a whole, it's easiest to resolve the forces into straight right and straight left. So acting on the system to the right, or pulling it to the right and down, we've got the force of gravity acting on the bucket. Okay, so that's the mass of the bucket, the full mass of the bucket, times g. Actually, we can get this value. Let's not do things over when we don't have to. We've already calculated that mass. Yeah, the total mass of the bucket here, 1.85. We've already calculated that. That's the mass that's just going to get the system to start accelerating.
Wouldn't that be slightly off?
Yeah.
Because the
Yeah.
0.5?
Yeah.
We have to add 0.
We'd have to add 0.01 to that.
Oh, okay.
Yeah, I'm not going to worry about that though. So it's 18.1 newtons.
We already knew that.
And acting against the force of gravity, or resisting the motion, is now the force of kinetic friction, not the force of static friction, because now the system's actually moving.
Watch it every day.
Yeah, that's crazy, eh?
We should watch more of an unchained reaction.
Oh, there it is, 0.34. And the normal force we calculated way back up here, 43.1 newtons. So it's 14.7. That's good. So,
Well, I love
there's
this
going to be a
one.
good background track in this
This was
video.
the best
Yeah.
song last
Yeah.
year.
Anyhow, so these are the only two forces acting on the system. Okay, we've got force of gravity going down, or I resolved it to going to the right, and then we've got friction opposing that. So we can figure out the net force pretty easily now. Oh, should do it down. I have to get the value, so it's just oh, what am I doing? Sorry, brain fart. But I can edit that out. So the net force is just going to be negative 14.7 plus 18.1 newtons. And again, that's using the fact that the forces to the right, we've always been calling positive, forces to the left, we've always been calling negative. .4 newtons. We're one step away from solving this last question. Is that gone? You tell me what it could be.
Acceleration.
Yeah. Okay, so the last step. Okay, and it's the total mass of the system. So 3.4 newtons divided by 4.4 plus 1.85. Oops. Okay, so question? No? 3.4 divided by 4.4 plus 1.85 gives 0.544 meters per second squared. that general direction. Any questions? Okay, so let me just review that. Okay, part A said what's the maximum, what's the force of static friction? That's just acting on this block. We don't even care about the dangling mass at this point. So just 4.4 times 9.81 multiplied by the coefficient. Then in part B, we realized that the tension applied from to accelerate the system, to accelerate the whole system, is equal to the force of gravity acting on the dangling mass. So we had to go down here and calculate what that force of gravity would be in terms of the mass of the bucket, then do some just grade school calculations to figure out how many washers that would be. We talked about the fact that was the problem with the experiment was the fact that you're adding a relatively large mass at a time, so you're gonna miss. You can't really calculate very accurately or with a lot of precision the force of static friction. And then here we put everything together to figure out the overall acceleration of the system using Newton's second law. Okay. Any questions? I'm Ray William Johnson. Thanks for watching.
This has been a Dylan Brewer presentation. Let the physics begin.